Okay, here's a question about a door. And there's a door closer, which is trying to close the door. And you have to apply a force to the door to try to keep it open. Okay. Let's prepare by drawing a sketch of this physical situation and trying to figure out really what the question is on about. Okay, so here's the hinge, and here's the door. And we're told that there's a door closer, and the door closer is applying a torque of 5.2 Newton meters. And I'm going to draw the direction of the torque like so. The door closer is trying to make the door move this way. What is the least force that you need to apply to the door to hold it open? Well, if you're holding it open, by that, we mean the door is not moving. And if the door is not moving, it's in equilibrium. And so therefore, the sum of the torques on the door is equal to 0. What that means is if the door closer is pushing this way with a torque of 5.2 Newton meters, you need to push back this way. You need to make a torque in the opposite direction, and the torque that you apply has to be 5.2 Newton meters as well. So you have to apply a torque of 5.2 Newton meters, and you want to do it with the least possible force. Well, if you're trying to do it with the least possible force, okay, let's remember our definition of torque. Torque is equal to R times F times the sine of phi. Now, phi is the angle between the line from the pivot to where the force is applied and the angle of the force. And we're going to get the maximum possible torque for a given force if sine of phi is equal to 1. So we can take this away and let it be 1. And for that to be true, phi is equal to 90 degrees. So we want to push perpendicular to the door, but that's not a huge surprise because that's what you would expect to have happen. The other thing we want to be true, if I want to have the smallest possible force to produce this torque of 5.2 Newton meters, I want to have my distance be as big as possible. Well, if I'm pushing this door, the farthest I can be from the hinge is at the very outside edge of the door. So clearly, I want to push perpendicular to the door at the far outside edge of the door. I'm going to be pushing at a distance of 0.91 meters out from the hinge, and I'm going to be pushing perpendicular to the door, and the torque that I'm applying is going to be 5.2 Newton meters. And with that, we have everything we need to solve the problem because the problem just asks for the force that you need to apply. Well, the force you're applying comes out of this torque expression right here. You're applying a torque, R times F times the sine of phi, but the sine of phi is 1, okay? And the distance is the distance from the pivot, and I want this to be as big as possible. Well, as big as possible is 0.91 meters. And the torque that you're applying is equal to 5.2 Newton meters. So I can just take this expression and solve for the force, and if I do that, I get 5.7 newtons to two significant figures. Now I'm going to notice a couple of things about this solution. First off, let's assess by thinking about the reasonableness of the solution. Okay, 5.7 newtons is a bit more than 1 pound. And a bit more than 1 pound seems like a reasonable force to apply to keep a door open if the door closer is not particularly vigorous. So that number matches our expectation of the way the world works. But also notice this, we're given the height of the door, the thickness of the door, the mass of the door. None of those make any difference. The only thing that makes a difference is the width of the door, because that gives us the distance from the pivot point where the torque is applied. And sometimes solving problems involves looking at it and figuring out what information is necessary and what information isn't.